So today I'm going to be talking about pistons before they go completely out of style and are not used and have been, being taken over by the GXVs and the higher SEER ratings and all that that's happening in our industry. So I was drawing on the board, so I got some pictures, how a piston looks as it sits inside the pipe as you're looking from the liquid line into the piston and the evaporator, how it flows through it. It's got the Teflon ring that helps seal and seat that piston inside the housing, where flashing takes place. So I drew some information for the guys I was talking to, but figured I'd put it out there as a just some good knowledge or whatnot. So here we go, all about pistons. Of course, I got pictures I'll pop up throughout the video, but pistons. Pistons are part of a fixed metering device family, along with things like capillary tubes. So these types of metering devices are, of course, like their name gives, they are fixed, okay? But what does that mean? Well, it means that the size of the opening can't change. If you look at TXVs, which have been around forever, and eventually we're going to go all electronic, I imagine, but those types of modulating metering devices can change the opening size and basically change the flow rate. So, but one thing I want you to keep in mind is that no matter what system I go to on a house, light commercial, whatever, if it's refrigeration based, then I'm still getting all my readings, all right? High side, low side, vapor line, liquid line, everything. Superheat, subcooling, like the whole workup, okay? But with a fixed metering device family, you're gonna be looking more so at the superheat reading, and with the modulating things like TXVs, you're gonna be watching a lot more of the subcooling per se. So that's just differences in the family, okay? But anyway, because the piston is what it is, and they can't adjust with any changing load on a system, or the seasons as they change and the load outside changes because of the weather, they're just so simple that there's got to be something that gives with them, right? So what I tell people when talking about a piston metering device is that the best time to check that system is on a hot day, right? Hot house, hot summer day, hottest part of the day, so 3 o'clock in the afternoon, no clouds in the sky. You left your beach umbrella, in the car because you went to the beach on the weekend, right? But you've got no shade in the yard. Like, we want it hot. So that's when you can check these systems, or you can charge these systems the best and get it right. And hopefully you get the point about the heat, right? So it's really all about pressure with these metering devices. So when we're dealing with the pistons on that system, it's the pressure that's going to help that refrigerant flow like it should, like we want it to, so that it does the job cooling in the house. So the fixed nature of a piston, okay, is just the orifice size. It's not a fixed flow rate. The flow is not going to be the same just because it's a fixed metering device, right? It's just the size of the hole that's going through there. Without pressure, okay, you can get some crazy numbers, and you have to decide what's going on with it. So, but how do we get pressure when we're dealing with refrigerants, right? We need heat, and that's why I say that heat comes from a hot day, a hot house. It's the heat load that you're putting on the evaporator and the condenser. Now, I say pressure, but it's more than that, right? It's not just high and low side pressure, okay? We're really talking about the pressure drop through that metering device, or the differential pressure. Matter of fact, if it's a piston, you got about a 1/2 inch right there. We're talking about the high side being on one one end of this thing and the low side starting on the other. So we're talking about the difference in basically, a finger wide, okay? The differential across that piston is what's important. So that pressure drop across the metering device, the pressure is going to move from high to low. We know that, right? The compressor feeds the high side of the system. It feeds the condenser, but pressure moves from high to low just like heat's going to move from warmer to cooler. So with a constant heat load on the condenser coil, just like you have on the hottest day with a hot house, in the middle of the afternoon with no shade trees in the yard, we get that heat that we need that's going to increase our high side pressure or the head pressure, okay? That increase in your condenser pressure and your temperature, essentially, your saturation point, is going to increase that pressure drop across the piston. Now, what happens when you get an increased pressure drop across the piston, right? With a larger pressure differential, you're gonna get more refrigerant flow through that opening, okay? So with that liquid coming in, the condenser's pushing, right? It's got a lot more pressure, it's got a lot of push behind it, and as it goes through that metering device, it's gonna make the flow happen better. You're gonna get more flow because you got more pressure pushing it, right? So when we get more flow through that real precise hole, that orifice, okay, the piston, whatever size it is, right? So 2-ton system, you got a 2-ton metering device. 5-ton system, you got a 5-ton metering device, right? Whatever size opening that is, doesn't matter, but the pressure differential is gonna drive the flow through it, okay? Because that condenser has more pressure and the flow increases, what's gonna happen on the low side, right? You're gonna get an increase in your evaporator pressure. Just a little bit, maybe not as much as the condenser, right? But an increase in pressure. What does that do to the saturation point? It brings it up. But that's not all of it, right? You have to think of it in that aspect about pressure to pressure kind of deal, but think about the flow rate. When I'm flowing better, when I'm flowing more, when I'm flowing like I should on a hot day, I'm pushing more liquid into that evaporator. I'm pushing more refrigerant into that evaporator, okay? So that's gonna affect it. It's also gonna affect the compressor, right? So you need to be taking into consideration the compressor amps, okay? So hopefully you know a little bit about the mostly liquid mix, right? The flashing or the flash gas that happens. Your metering device is one of two places where the pressure changes in a system, the compressor being the big one, the motor, it goes from low side of the system to high side, but the piston drops it from high back to low, okay? So we have a mostly liquid mix of refrigerant that leaves that piston, and when we have more liquid with that flow pushing in, right, I think about it like this, okay, on the evaporator coil. I try to think about the two states of refrigerant, right, liquid and vapor, just like a coin. I've got two states, and I've got two sides of a coin, okay? So when I hear one, I think about the other. So if you say more liquid, what's the back side of the coin? Less vapor, okay? When I say less liquid, I think more vapor. So in the case of we'll say proper normal refrigerant flow going on this warm day with a warm house kind of deal, when I say more liquid going into the coil, what I'm thinking on the back side of my head is there's less vapor in the evaporator. Like I'm filling my evaporator up and it's being active, it's being effective, okay? So keep that in mind. But less vapor means what? That means that we have less superheat, all right? You have a lower superheat. Think of a number and call it normal. I'll just say 8. If I said 8 degrees of superheat to some people, they'd be like, oh, that's way too low. I need 15. Well, and maybe you'll get there, but on a piston, I think of a hot day, providing that the unit's perfectly charged and all that, like it's normal superheat. And this is why you should keep records of things, as you're doing these calls, okay? So less vapor means that this increase in flow and increase in the low side pressure, you're gonna get a lower superheat. Like I said, you call it normal, but to get the normal, you got to have the heat, you got to have the pressure. So I wish that nobody has an issue with their air conditioner, but if it's a piston system that I'm going to go to and work on, then I need a hot house. I need a hot day. I need no shade in the yard, right? I need to have some sunscreen on, kind of deal, all right? And that's going to help me evaluate the refrigerant better. It's also going to help me with the compressor, right? You got to watch for the compressor too. Don't forget about the compressor. When I have more refrigerant and more liquid, which means less vapor and less superheat, right? That's fine, but think about the compressor. I'm having to move more refrigerant. So with the compressor, you're probably going to notice that the amps are going to go up because I'm moving more refrigerant, okay? More work on the compressor is more amps. That's just what it is, all right? So before I get too far, right, if you're watching this in the summer, like, stay hydrated. That's my safety public service announcement. So back to it. But so be thinking about that with a piston in your hot part of the year, right? Now let's switch gears and go cool part of the year, or lighter load conditions. So what about when we change the season, and let's say it's fall, right? You get a weird call, but it's fall and the weather pattern's real nice, or it's springtime and same, right? Real nice weather, right? Little sweater weather, cool mornings, kind of warm afternoons, but it's not hot, right? Let's look at the condenser again. Mild weather means you're going to get less heat, so that's less pressure on our high side, which means we're going to get lower pressure, on our low side. Okay, we get less of a pressure difference across that piston. Okay, what's that going to do? This means that because there isn't that pressure that's going to push the proper amount of refrigerant in there, then just like we did in the summer, same unit, different days, different months, right? But with a reduced pressure, you basically get a reduced refrigerant flow because there's not that pressure in the condenser to push into the evaporator, right? You're going to get a lower low side pressure, lower saturation point on your evaporator, but not everything's low, right? No, the flow rate is low, but low flow rate means what, right? It means we're not getting as much liquid, which means we're getting more vapor. So if you check your superheat on a mild day like this, same unit from the summertime, you're very likely going to see high or elevated superheat readings because you have less liquid being pushed, less being flowed, if I could say that, through the metering device and into your evaporator. So more vapor, more superheat. That reduction in refrigerant flow, right? If we think about the compressor, we got less to pump, so less is moving. So your compressor's still moving and generating some heat. So while the amps may be down, it might be warmer on the shell of that compressor because you're not cooling it off, right? The same refrigerant flow that keeps you essentially cooling is also going to keep that compressor, in check in temperature range and stuff, and keep it kind of safe. So without that flow, it's not good for the compressor either. All right. So think about that. Keep it in mind. Do some research and some homework on it. But let me tell you, I hate to go quick story, but I'm gonna give you one, maybe two. So when I was a younger apprentice, we'll say, and I'm not saying this to point fingers. I hope nobody knows who I'm talking about, but like, true story, okay? I'm not doing this to say I'm better. I made my mistakes and learned, okay? But you got to read, you got to understand and ask questions, right? So once I was working for a newer company, and the guy that I was riding with, we'll call him the senior technician, we got a call for a maintenance or for an air condition check. Now this is April, okay? So not the fall, it's just the same thing in the spring, right? But it's April, okay? We pulled up like mid-morning, okay? We weren't there for an air condition issue. Why were we there? We were there for maintenance, okay? Just a little cleaning, a little prep for the summertime, okay? Here in the Southeast, the summertime is usually brutal, so we knew it was coming, so the lady was, letting us do that. Maintenance programs, just so everybody knows, a plug for the industry, I guess. Maintenance programs keeps everybody going. The customer's gonna get a better deal on capacitors and whatever, right? Little things that may be needed to be addressed. And the air conditioning guys, they get to have a full paycheck. So it's good for everybody in the slow times of the year. So a lot of companies do maintenance agreements and it's just a win-win for everybody, okay? So anyway, we're there looking at everything. The electrical stuff looks good. Did the coil cleaning with the coil cleaner and the water and everything like that. And then we turn the unit on because it should run before you touch it, and it should run as you walk away from it. And we start checking refrigerant pressures, okay, with everything clean. But keep in mind, we just sprayed it with water, so the coil is wet outside. So that's going to be some conduction, and then you turn the unit on, and that's forced air movement, convection. Okay, we kind of got a double whammy on the condenser coil, and it's April. So guess what? All right, everything is cool and nothing is warm. So we're kind of running it, but the pressures were way low, right? So we let it run 15 minutes, okay? And after it warmed up, the tech was like, all right, let's check everything and record our numbers. So he starts recording his numbers, gets his high and low pressures, his superheat, subcool, his line temperatures. We're looking at return and supply temperatures, doing the whole workup. And then he looks at me and he was like, John, go get the jug. And I'm like, yes, sir. Now he's the primary guy looking at everything. I'm there as a helper. But I jump back to the van, I go grab the jug and scale, right, weigh everything. And now he's the one, we weighed it first, the way that his style was, he weighs it first, and then we weigh it at the end and still record how much was taken out. So we weigh it, and then I bring it to him, and he adds a pound. So he puts in a pound, waits a minute, 10 minutes, 5 minutes, whatever it was, but he waited. No change, right? So he puts in another pound. Wait a few minutes, another pound. And he did this repeatedly, okay? And then finally, I didn't know if it was confusion for what he was looking at, or he just made a decision that, hey, that's enough, okay? So he says, hey, what is the proper charge from the manufacturer data on this thing? And I look at the data plate and I say, hey, it says right there, 7 pounds, 2 ounces. Well, once he weighed his jug, he realized he put in 7 pounds. And guess what? It didn't change, okay? Like I said, he kind of looked at his stuff because he knew he had been adding, but the pressures weren't moving at all, okay? Hardly any, it's just negligible numbers. Superheat's still the same, the pressures were the same, like it's all the same, okay? So he looks for a minute and was like, okay, and we like wrapped it up, and I'm like, man, this is an issue, okay? But pretty much as we were finishing up, okay, like the decision, I guess, in his head was like, enough's enough. So we're ready to go to the next call, okay? Fill out the invoice and get done, okay? I won't tell you any more, and I won't tell you any names, but here's my point, right? The technician wasn't thinking about how the system was working, not taking into consideration that he was basically working on a fixed metering device system, and he was adding refrigerant, and the fact that it didn't do anything, I think, kind of messed with him, okay? So now if you think about what I said, he added 7 pounds, and the factory on the label, they called for 7 pounds and 2 ounces, right? So what should have probably happened, so if I ever had to add 7 pounds to a system that only held 7.2 pounds, my mind is, when I put my gauges on there, low side 0, high side 0, right? Why would I add that much refrigerant to a system? If you come across a situation like that and add that much refrigerant, then, like I said, your gauges should be basically on 0, and you shouldn't be starting by adding refrigerant. You should be starting with a leak search, because there ain't none there, right? But there was something in that system. There was a little bit of pressure, and it wasn't an issue at first, so he turned it on and, and went from there. But yeah, so he added refrigerant on a very mild day on a system that was fixed, okay? The inside of the house was 74, the outside of the house was 74, okay? And what that meant is this, he saw pressure lower than what he thought, okay? Lower than what he wanted, in his mind, but that's because it was April, it was mild weather, okay? When he looked at his stuff, he saw low pressure, on the low side. He saw a high superheat reading, and anybody that's done heating and air or dealt with a heating and air guy, right? If you have low pressure on the low side with a high superheat reading and the compressor's not really pulling any amps, right? Guess what? Number one problem in the world, low freon. It's always low freon. Anyway, all right, so instead, this guy had a piston system on a mild day that didn't have any problems, right? The system charge from all your practical, logical reasoning would have been correct. Definitely didn't need to be touched, but he essentially doubled it, right? 7 pounds, 2 ounces on the data plate, and I just put in 7 pounds. You doubled it, okay? All the readings pretty much stayed the same. All right, superheat, subcooling, like nothing really moved. Maybe the subcooling, I forgot, but I remember the rest of it pretty good, right? So instead, there was a piston in this system, and it was a very mild day, and there were pretty much no problems that we really knew of. Got lost in the readings, right? The superheat was too high and the pressures were too low, but you lost track of the basics, okay? From all practical, logical, reasoning, everything was fine in that system, and it didn't need to be touched. But the decision was made, and it was. So the charge on that system was essentially doubled. Not a doubt in my mind that it was double, because it would have been 0 PSI if it would have been empty, right? So we put 7 pounds in on a 7 pound, 2 ounce charge, data plate reading, and nothing moved, all right? If you left that system like that from April and then you get into July, what's gonna happen, right? It's gonna be game on. Pressure's gonna be through the roof and everything, right? Because now the heat is gonna make this really come into play, and you're really gonna feel the effects of it, okay? So pressures are gonna be through the roof, there's gonna be liquid going back to the compressor, the amps on the compressor is gonna go high. Like, it's just a bad deal for the customer if that were to be left in that condition. So now let's flip the scenario and put the heat somewhere else. Let's say that it's the fall time of the year and we're gathering together with family and friends at some holiday. We'll call it Thanksgiving. The evaporator is going to have more heat as a load than the condenser, okay? The people load on the evaporator when we get together, right? The body heat, the humidity from the sweat and stuff like that is more of a load to the evaporator. And outside, if it's 50, 55, 60 degrees, right? Depending on, where you're at and exactly what's going on. But in this scenario that I'm laying out, you have a much higher load on the low side. So you're gonna have higher pressures on the low side, more than normal. But because it's so mild outside, think about that. The condenser is not gonna really have any pressure. There's also, now what this does, right, back to that pressure differential across the piston, that lowers the pressure difference. Condenser is still gonna be a higher pressure, but not much higher, right? And the evaporator is basically rising up to kind of meet it. So you're gonna lose that pressure differential that you had. And when that happens, you get a reduced flow, you're gonna get high superheat, which means you're killing the compressor. The same refrigerant that cools you off cools that compressor off. That's the basics of it, right? Low flow of refrigerant, you get high superheat, you're gonna get a hotter compressor. It's just a bad deal all around. So try to pay attention to the type of metering device and the conditions that you're going on. So anyway, all that said, right, here's what's really going on and my purpose for the video. Yet another story, okay? So I recently had a fairly new technician come up to me, and he was giving me some numbers, some information about a unit that happened to be on his particular house. And as the conversation went on, and of course in heating and air we know people, so everybody started coming in, and everybody has their own 2 cents worth of input. But as the guy who was actually diagnosing this on his own, he he had his numbers. He had amp readings, he had volt readings, he had superheat, he had subcooling, air temperatures. Like, he did everything that you need to start troubleshooting, I'll say, his unit. And another technician, he threw his hat in the ring and basically came up and said, what about the wrong size piston installed in your air handler? What I've got here is I've got a 3-ton Goodman unit, a heat pump that we're going to be on. It's a 3-phase setup, but that's only for the heater kit. The blower motor on that one is a single phase PSC motor, you know, capacitor, all that stuff, just, you know, pretty standard. I verified the airflow with kind of a fancy airflow kit that we have around the office. This unit doesn't have a lot of duct work, so the numbers are a little low on the bottom end, but you'll get the idea, right? At least I know what it is. It's right about 340 CFM per ton instead of the 350 to 450 where we average and get a 400, right? But just so you know, I did check it, okay? Everything is on the up and up. I'll show you, you know, a little report or whatever from the printout. So to calculate the airflow, we used a static pressure test kit that we have in the office, and it came with several different sized return grill inserts that you would place inside the unit, and it had an app to go with it and everything. So I used that versus a electric heat CFM calculation and just thought it would be a better number to establish with. And as I went through and put it on low speed, you can see the static pressure reading here on the little report, and I got my CFM for that. I then went to medium speed, same thing, static pressure reading, and I've got my calculated CFM for that. And then last I went to high speed, and of course static pressure, I got my CFM calculation for that. So it's all in the little report. I wound up going with high speed, of course, because it was better suited. I was trying to get to at least a 1050 CFM airflow number, but I wound up being just a little short at about 1020. So we're not quite 350 CFM, but I do have 340. I know what it is, it's set, and I'm happy with it. I did 4 sets of readings with 4 different pistons. I've got a 3-ton unit, okay? So keep it logical, right? I got a 3-ton, you know, piston basically. So I did one with a 52, which is for a 2-ton. I did one with a 65, which is for a 2.5 ton. And then I went all out and did an 83, which is for a 5-ton unit. And then I finished it up with the one that was supposed to be there, which is a number 72, which is made for this 3-ton air handler, okay? That's what the manufacturer called for in the literature, and that's what we left in it, right? So I started and did all the other ones first and just left it running with the correct piston on there. If you didn't know what size it was, Goodman actually stemples on the side of the nut, right, where the Teflon ring that actually holds the piston in. They actually kind of dimple or stemple the size on there. So kind of hard to mess up. So I tried to do it by the numbers, ABC, right? Airflow before charge. It's there. I got the airflow down. I recovered all the refrigerant every time. I vacuumed the system down to 1,000 microns or less. Every time we did the piston change, I used a torque wrench to torque the nut down for the piston. Everything's there. I don't think I missed anything, and if I did, it wasn't intentional. I'm gonna run it in cool mode. So we're gonna be looking at the air handler, and what I've done is I pulled up the product specs for that particular model number. So I know I've got the right piston. And what I'm gonna do is I've already, well, here's what I've already done. I've completely recovered this unit. I have measured the line set with a tape measure. I have pulled a vacuum on it, and I have recharged it 100%. Okay, there's no known issues on this unit. It's a 3-ton, it should work as 3 tons. And if I do everything right, like I want to in my head, I'll have a nice little chart You can pause the video, look at it the whole nine, but each time that I change out the piston, I'm gonna pull a vacuum. We're gonna make sure there's no leak. We're gonna kind of do it as close to textbook as we can. So I hope you enjoy this. I look forward to some questions, comments, whatever. But this will let you wrap your head around what it looks like when you have the wrong metering device. All right, round one. It's a little warm out here today. It's about 75 degrees or so, so it's not, you know, a hot summer day. I've got our low and high side pressures. Superheat and subcooling look good, 13 to 14 apiece. Compressor amp side already taken, about 8 amps. So, so far so good. So after every time I change the piston, I am pulling a full recovery and a vacuum. And in this case, I'm recovering the 9 pounds that I charged in previously. And that's because I can't pump this unit down. There is a pressure relief safety in the compressor, and I can pump it down to about 85 PSI, but then it cuts off and you can hear it bypassing and everything inside. So after each time I change the piston, full recovery, change the piston, we're gonna pressure test, pull a vacuum, the whole nine. So that's what I'm doing right now. Got hot enough out here that the tank started getting warm, so I had to break out my ice bag. So use the ice to help you drop the pressure in the tank. Kind of curious on this one. So I did the first round of checks, and now I just finished a recovery because I couldn't pump this unit down. And we're gonna see what size piston was in here. That's an 065. 065 is in there. I'm gonna put an 051. So that's a 2-ton metering device. So I'm gonna put that in, torque this back down, pull a vacuum. It's gotta be between 7 and 25 foot-pounds. So 18, 20, something like that. We'll start there. Make sure this don't twist. So my wonderful piston chart that I made to compare the piston information that I got as I ran all these different scenarios. So it's fairly self-explanatory. You can see that I've got the piston size in the far left, and as you go across the top, you're looking at low pressure side with the evaporator saturation, the high pressure side with the condenser saturation. I've got superheat, I got subcool, I got a delta T, return and supply, dry bulb numbers that is. I've got a wet bulb set of numbers there as well, so the return and the supply. And what I did with that is, if you look at that next to the last column, I calculated for enthalpy. So I've got a delta H, and I've got a chart at the end of the video that will walk you through that formula and that little process with a chart and everything. So, and of course, last is the airflow. So constant airflow, I didn't change the speed once I found the right one. So it's about 1020. Down at the bottom, you can see that I have ambient information for the outside weather. I've got the return air for the inside going into your evaporator coil. I've got a measured length for my line set, and that's 61 feet for this particular unit. Standard numbers to go off of for a new air handler system is going to be 15 feet. So when they tell you that you need 10 pounds of refrigerant or 5 pounds of refrigerant or whatever it is, they're talking about in a split system configuration, you got 15 feet of separation between the outdoor coil and the indoor coil. Anything above 15 feet of separation, you're going to have to adjust the charge and add more refrigerant. And technically, if you're below 15 feet, you really should be taking out refrigerant, but we'll talk about that later. So I've got a factory charge of 112 ounces, and that's good for the indoor coil, outdoor coil, and 15 feet of line. In my measured line set length, I've got 46 extra feet. So I need more refrigerant. And you can see there that I have an additional charge listed as 27.5 ounces. So I used a formula and a factor, I should say, of 0.6 ounces per foot for a 3/8 liquid line.
and I took that 0.6 ounce and I multiplied it by the 46, and I came out with 27.5 ounces. So I had my factory with my additional charge for the compensation of the extra line, and I get a total charge that's right at 8 pounds and 12 ounces. But in the video, as I told you, I put in 9 pounds. Why? Because I know my hoses are going to hold 1.5 ounces, maybe 2 ounces, depending if it's liquid or not, of refrigerant. So for me to keep it simple and just have a nice round number, it worked out well. Usually I charge a couple ounces over what I calculate anyway, because I know my hoses are going to come off and my hoses hold a little bit of refrigerant. As you look across, you can see the 51, that's my 2-ton size and all the information. My 65 is my 2.5. My 72 is going to be my 3-ton, which is called for. And my 83 is going to be my 4, maybe 5-ton piston. I just had it in the box and threw it in there, right? So all the information listed there. What I tell you to do is compare the 51 and the 83. That's the smallest and the largest pistons that I used. And if you look, you see pretty drastic numbers, you know, as you compare those two sets of values. That's to be expected. But what surprised me personally was the 65 and the 72. The 65 being made for a 2.5 ton, and then the 72 being the one for this 3-ton. The numbers were pretty close. They weren't that far off, and you can see that information listed there. And if I stopped at the delta T and I didn't do wet bulb numbers, what you would probably agree with me with, or agree with me on, is the 65, the 2.5 ton piston, seems to be the better choice. And if we run some wet bulb numbers on there, it's got a delta H of about 10.1, which, you know, isn't bad. But the 72, even though the superheat, you know, dropped drastically, I mean, they're almost tit for tat the same, except for the superheat value and the delta H number. So even with a 1.6 degree superheat, when I factor in that delta H number in the enthalpy chart at the end of this, it seems to be it's good. The 72 is a good choice. So, and of course it's going to be there and allow more flow in a hotter environment. So this was very mild weather. I did it on purpose that way, and I thought it worked well. So here's the chart. Compare the numbers, do your homework, ask some questions, but I thought it turned out pretty well.
That was everything. Well, not everything on pistons, but something to get you started. They will be, I'm sure, phased out eventually, but for right now, there's still quite a few of them out there. So I hope this little bit of information helps. Thanks for watching, and we'll see you next time.